In our previous lesson, we were graphing linear inequalities. And so here's a quick warm-up to review. To the right is the graph of the inequality y is greater than negative 2x plus 4. Can you identify a point that is a solution to the inequality? Can you identify a point that is not a solution to the inequality? And is the point 2, 0 a solution to the inequality? Explain why or why not. So take a moment to answer those 3 questions, and then we'll check your results. First question was to identify a point that is a solution to the inequality. So for our inequality here, y is greater than negative 2x plus 4, none of the points on the boundary line would be considered a solution. So the only points that would be solutions are included in the shaded region. So our shaded region is here, okay? So everything kind of to the right and above our boundary line, not anything on the boundary line, could be a solution to our inequality. So we do have an infinite number to choose from, but they have to be in that shaded region. Our second question was to identify a point that is not a solution to the inequality. Well, that could be any of the points along the boundary line or in the non-shaded region. Again, there's an infinite number of points that fit that criteria. So anything that's not in the shaded region or on the boundary line are not solutions to the inequality. Our last question is the point 2, 0 a solution to the inequality? Well, here's our point 2, 0, and as you can see, it's on the boundary line, so it would not be a solution to our inequality. Remember, the boundary line, when it's dashed, shows that those points are not included in the solution area, so it would not be a solution to our inequality. So with that in mind, we know that not everything is individual, right? A singleton. We can start putting things together where we did systems of equations, and we could do the same thing with systems of inequalities. So we're going to practice graphing systems of inequalities and finding their solutions. Now, when we're graphing a system of equations, we saw that we could have a solution where the two lines intersected. We could have no solution where the lines did not intersect, and we could have infinite number of solutions if they happen to be the same line. So for us, kind of the same rule will apply with our systems of inequalities, but our solution, because they're inequalities, will be a shaded region. So we're looking to see, by the time we graph each inequality, what would be the shared shaded region, and that would represent our solution set. If there is no shared shaded region, then that would be no solution. So we'll keep those things in mind as we go through. So let's take them individually and see what they look like. So our first one here, y is greater than negative 3x minus 1. It's already in slope-intercept form. So we know our y-intercept is at 0, negative 1, and our slope is at negative 3. So if we use a scale of 1 here, 0, negative 1 is here, and we go down 3 units into the right one and put a point, down 3 to the right one, put a point. We also go from the y-intercept and reverse it, up 3 into the left one, to create points for our boundary line. Now, will our boundary line be solid or dashed? We're going to look at our symbol, and we can see because it's got the equal to, those points are included, so we're going to have a solid boundary line. Now we need a good test point for shading reasons, and we could see 0, 0's perfect fit because it's not on the boundary line. So if we put 0 in for y and 0 in for x, what happens? Well, we would have 0 is greater than or equal to 0 minus 1. Well, 0 minus 1 is negative 1. So is 0 greater than or equal to negative 1? It sure is. So we're going to shade on the boundary line and above for our solutions for our first inequality. Then we look at our second inequality. Is it already in slope-intercept form? Yes, it is. What would be the y-intercept? Well, that would be at 0, 2. So we're starting here. What's our slope? 1. We're going to go up 1 into the right one and put a point, up 1 to the right one until we run out of room. We can also go back to our y-intercept and reverse our slope, going down 1 into the left one to plot some points. And then we can see how are we going to connect them. Again, go back to the inequality symbol. It's just less than, so that means these points are not included, so we're going to use a dashed line to connect them. Now we have to start working on the solution set. So let's again, great test point is 0, 0, because it's not on that boundary line. If we put 0, 0 in here, we'd have 0 is less than 0 plus 2. Well, we know 0 plus 2 is 2. Is 0 less than 2? It sure is, so we're going to shade on the side of our test point 0, 0. So we've graphed each inequality. Because it's a system, we're looking to see what they have in common. So we want to see blue and green shaded regions, same place, same time. Do you see that happening? Sure we do. So if we take our pen here, we can see everything below our blue line here in quadrant 1 of our graph and a little bit into quadrant 2. And then everything on our green boundary line and to the right of that would be a solution set. So we're looking at solutions mainly in quadrant 1 and 4 and a little bit into 2 to represent that. So we want to go over that in a very dark color to show where all those solutions lie in that solution area. So any part here on this portion of our green boundary line would be a solution, and to the right and above, but not including what's on this portion of the blue boundary line. Let's take a look at another. So here we want to graph our system of inequalities. Let's take a look at the first inequality. Is this in slope-intercept form? So is y isolated? No, it's not. So we're going to have to do some work to get y alone. So can you do that and enter your results into for a check? So to undo this inequality, we would have to undo this 2x. We'll subtract 2x from each side. Then we'll have to divide every single term by a -3. So remember, when you're doing that, you're taking the opposite of each piece. So a negative divided by negative would be a positive divided by a negative is a negative divided by a negative is a positive, and that's impacting your inequality symbol. So remember, instead of being greater than, it's now. So now that y is isolated, let's work on graphing. So our y-intercept comes from this portion of our inequality, and we know we're starting at 0, -3. So that would be here, and from this point, we're going to move according to our slope. And our slope is 2/3, which means we're going up 2 units into the right 3, putting a point, up 2 units into the right 3, putting a point, and continuing until we run out of room. We can always go back to the y-intercept and reverse the slope, going down 2 into the left 3 to get some more points to generate for our boundary line. Now, what kind of boundary line do we need? Solid or dashed? We look at the inequality symbol for our hint, and we can see, because we just have the less than, we know that those points are not included, so we need a dashed line for our boundary. Where are the solutions for this inequality? We have to pick a test point. So if, say, we pick the test point 0, 0, what happens? So if we put 0 into, we could say the original inequality if you wanted. 2 times 0 is 0, -3 times 0 is 0, 0 minus 0 is 0. Is 0 greater than 9? No, it is not. So we cannot shade on the side of our test point 0, 0. We're going to shade on the opposite side. So not here, but down below our boundary line. If you wanted to use this inequality, you could do the same thing. And it would, again, 0 is not less than -3. So we're shading below the boundary line. Now we go to our second inequality and say, okay, is that in graphing format? And it is. We're starting at 0 and our slope is 4. So we're going up 4 into the right 1 until we run out of space. Then we can go back to our y-intercept and reverse our slope, going down 4 into the left 1. So we have a good set of points now to form our boundary line. Well, what kind of boundary line would we have? Look at the inequality symbol for your clue. We can see the equal to, so it would have to be solid. So we're going to connect those points with a solid line. Now we've got to look at our solution area. So we got to do some shading with the test point. We cannot use 0, 0 for the test point because it's on the boundary and we already know that it's included. So we're going to have to use something else. So instead of 0, 0, why don't we use 1, 1 to see if that's true or false. So put 1 in for y and 1 in for x. If I do that, is 1 greater than or equal to 4 times 1, which is 4? Is 1 greater than or equal to 4? That is false. We're not going to shade on the side of the test point 1, 1. We're going to shade on the opposite side. So it's everything on the boundary line to the left. So since both inequalities are graphed, we want to find the solution area. So we're looking for the two colors at the same place, same time. And we can see that happening here mainly in quadrant 3, below the blue dashed line and up to and including this portion of the solid green part of our line. So that represents our solution area. So anything in the red space or on this portion of the green solid line would be a solution to our system. Let's try another one. Here we want to graph the system of inequalities. Remember, system just means two or more. And so you can see here we have 3 inequalities to work with. So why don't we start with our first inequality, y is less than 4. That's already in slope-intercept form, and we know the y-intercept is at 0, 4. So that would be here if we have a scale of 1. Our slope is 0, which means we're not increasing or decreasing. The outputs all are 4. So I can plot several outputs of 4 for points to form my boundary line. How are we going to connect those points? So again, look at the inequality symbol. We can see that it's less than, so we know that those points are not included. We're going to have a dashed boundary line. So here's what our boundary looks like for that inequality. Now again, we want to think about shading. So what would be a good test point? 0, 0. So if we substitute 0 in for y, is 0 less than 4? It sure is. So everything below our boundary would be considered a solution. The second inequality, x is less than 3. So x being isolated, we know that the slope is undefined. This is going to be a vertical line, and we have an x-intercept at 3, 0, which would be here. Now, if the x-intercept is 3 and we have an undefined slope, that means we're not going left or right, we're just going up and down, so all the x inputs here have to have a 3. So I can plot a couple of points here where the inputs are 3, above and below, along kind of that vertical line here. Now, as I'm plotting those points, do I want to connect them with a solid or dashed line? Look at the inequality symbol for your clue. There's no equal to, so again, we need a dashed boundary. And we can still use the point 0, 0 as our test point. So if we put 0 in for x, is 0 less than 3? That's a true statement, so we're going to shade on the side with 0, 0. That means everything to the left of our boundary line in blue. We have one more inequality to graph, which is y is greater than or equal to negative x plus 2. So our y-intercept is going to be at 0, 2, so that's starting here. And our slope is negative 1, which means we're going down 1 to the right 1 to put a point. We can generate a series of those. The question is, am I going to connect them with a solid or dashed line? Go back to the inequality symbol. We see that it's equal to. That's telling us it's solid because those points are potential solutions to our inequality. Then we're going to look at shading. 0, 0 is still a good test point because it's not on the boundary. So if I put 0 in for x and y, what happens? Well, this would be 0 plus 2, which is 2. Is 0 greater than or equal to 2? No, it is not. So we're going to shade everything on the line and above for our solution set. So with these 3 rules for our system of inequalities, we're looking to see where are they true at the same place, same time. So you want to see blue, green, and purple all in the same region. Do you see where that's happening? That's happening in quadrant 1, a little bit in quadrant 2, and slightly into quadrant 4. In fact, they're making a triangular region. All the points on that portion of the purple line are included up to but not including the portions of the blue and green lines. But you do have an infinite number of points in your solution area. So we've done some graphing of inequalities when the rules were given to us. Could we go in reverse? If we give you the solution area, could you write the system of inequalities to make that true? For example, here we have the shaded region. This is the solution to our system of inequalities. Could we write the inequalities that represent them? So let's highlight these boundary lines in colors. And let's take a look at this blue boundary line. Could we write a mock-up of the inequality equation, we'll call it, that it represents? So we know we'd have a y, some kind of symbol, so I'll put kind of a box to hold its place. Do we know the y-intercept and the slope? Well, the y-intercept here is at 0, 2, and I can see some other points on my boundary. And if I put a marking here, and here, and here, and here, we can see that our slope is always going up one and to the right one to get to the next point. So we know that our slope is 1. So I could write this boundary, we'll call it inequality equation, as 2 plus x, or maybe you wrote x plus 2, or 1x plus 2. This is our basic mock-up for our inequality equation, we'll call it. Could we do the same thing for our green boundary? So if we look at our green, again, could you see the y-intercept? It's crossing the y-axis here at 0, -3. And what do we know about the slope? Well, we do have all these points on the boundary, and we know they're not included. But to get to point, we're not going up or down. We're just going right and left, right? All the outputs are the same value. So that means our slope is 0. So we're going to have y, then I'll put a box to hold the inequality space, and our -3, if you want to put plus 0x, you can, but we don't have to because we know the slope is 0. So now that we have the inequality equation templates, let's try to work on finding the inequality symbols that go with them to generate this shaded area. So we're going to look at the test points and see what's happening. And what's a good test point that's not on either boundary? You got it, 0, 0. Now, when we're putting in 0, 0 for x and y, what would we have? Well, for our blue one, we have 0 compared to 2, and our green one, 0 is compared to -3. Now notice, 0, 0 is included in the shaded region for where that blue boundary line goes, right below, as well as for the green one. So when we fill these in, we have to have true statements with the inequality symbols. Also, the blue line is solid, so we already have a clue there that we need an equal to as part of our inequality symbol. So we're going to put that in. So as we think of these results, right, we're comparing 0 to 2 and we need it to be true. What kind of inequality symbol would we need there? Well, 0 is less than 2, so we need a less than or equal to. Again, we need a symbol here to be true when we compare 0 to -3. We know 0 is greater than -3, so we're going to need that inequality symbol in that spot. So now we know what symbols we need to make the inequalities true. So if we go back up to the top, let's replace what we know here to complete our inequalities. We know that y has to be less than or equal to 2 plus x, and y has to be greater than -3. This is the system of inequalities that generates this graph of the shaded region. Let's try another one. Can you write a system of inequalities from this shaded region? Again, think of your problem-solving process. Outline each of the boundary lines in a different color. Can you start writing the inequality equation template for each boundary line? Well, let's start with the one in blue. Can you find the y-intercept? That's here at 0, 1. Can you work on finding the slope? So if you look for other points on the boundary line, you can see you're going down 1 to the right 1, so your slope is -1. We can write that as y, and then we'll put a box for the inequality symbol, 1 minus x. Maybe you want to write it as -x plus 1, saying the same thing. All right, can we move on to the green boundary line? So where does it appear the y-intercept to be? Here at 0, 1 as well. What's the slope? Well, we can see we're not going up or down any. All the outputs are at 1, so our slope is 0. So our mock-up inequality equation is going to be y is something to 1. Now look at your purple. What do we know there? We don't have a y-intercept, but we have an x-intercept at 4, 0. And our slope is undefined. So this is going to be an x equation. So x is something to 4. Now, as you look at the shaded region, we want to have a test point, right, to help us. And so we usually kind of use 0, 0 as our test point. We can do that. And notice how it's not in the shaded region. So that's important. If it's not in the shaded region, that means as we're going through and working on simplifying these, we need them to be false statements. So let's kind of work on that. If we use 0, 0 as a test point, let's substitute those values in for x and y and simplify. And again, we have to think about 0, 0 and the meaning of the shading. So this blue boundary was shaded above, right? And 0, 0 is below, so that needs to be a false statement. And in the green one, again, it's above 0, 0, so that's false. And then our purple one, if we look at the shaded going to the left, that one happens to be true. So we want it to be true when it's 0, 0. So this is kind of our guideline. Then you also want to think about the type of inequality symbols. So do you get other clues with those lines being solid or dashed? The blue one is solid, so we need an equal to as part of it. The purple and green are dashed, so we do not need an equal to as part of the inequality symbol. So let's finish this up. 0 compared to 1. Well, we know 0 is less than 1, but we need it to be false, so that's going to be greater than. So we need the greater than or equal to symbol there. How is 0 compared to 1? Well, we know 0 is less than 1, but we need that to be false, so again, we need the greater than. 0 to 4, this needs to be true. 0 is less than 4, so we need the less than symbol. So let's take these inequality symbols and put them into the templates. The inequalities that make up this solution set would be y is greater than or equal to 1 minus x, y is greater than 1, and x is less than 4. Now it's going to be your turn to practice graphing systems of inequalities and trying to write the system of inequalities based on the solution area given.